Okay, thank you so much. Thanks, David, for the introduction. Thanks to you all for being here despite the great weather outside. Unfortunately, none of the other, actually, the student that was expected to be here could not make for visa issue, but I'm happy to take over and present our work, Kronos, secure sharding, generic sharding blockchain consensus with optimized overhead. So let's go through some introduction. So we know how blockchain works. So basically, at the bottom, we have this consensus protocol, which is BFT, Byzantine fault tolerant, or proof of work, or other things. And with this, nodes reach consensus. What is the issues with this is that it's poor in scalability, meaning that if we increase the number of nodes in the network, then all the nodes, again, need to be involved somehow in finalizing, confirming the transaction. So because of this lack of scalability from this point of view, in 2016, work CCS paper, I think, proposed sharding, so basically organizing the nodes into shards, and then nodes into shard will take care of transaction inside its own shard. So we will have, in this way, improved scalability, and we will have two types of transaction. There will be the intra-shard transactions. It means all the input and output will belong to the same shard, and this will be easy to handle. And the other type of transaction will be the cross-sharding transaction, where we will have input and output belonging to different shards. So as you see here, input 1 and 2 belongs to shard 1 and 2, and then output will be a different shard. Why we need to take care or be careful with this transaction? First of all, because the amount of this transaction is going to be quite high. So as you can see from the right part of the slide, it seems that in terms of amount, translation in US dollars, in Ethereum, the value of multi-input transaction, including the high-value crowdfunding ones, is estimated, or was actually 1 billion in 2024. And according also to some simulation, this Infocom 2022 paper on the left part of the slide, as soon as we go beyond 16 shards in a blockchain, then the number of inter-shard transactions goes easily above 90%. So we need to be careful about the cross-shard transaction because mostly of security and consistency. Particularly for security, we need to take care of the atomicity. It means this all or nothing principle. So let's take a look at an example. As you can see here, we have a transaction alpha involving unspent transaction output 1 and 2 that belongs correspondingly to shard S1 and S2. So in this case, we have a successful transaction. Then all of the information will be correctly committed in the output. This will be the output state. But another scenario is the one of non-successful transaction. In this case, we have transaction beta, where we have unspent transaction output 3 and 2, but 2 have been already spent in the previous transaction. No, this cannot be a valid transaction. And what we want in such kind of cases is that should be the nothing outcome. So all the shards should not commit anything. So we don't want partial transaction to be committed. Another issue with the current solution is that they are based on two-phase commit. What is a two-phase commit? Basically, we have a preparation phase and a commit phase. So in the preparation phase, in this case, you can see basically we want to spend the blue and purple coins to payees, which is in the shard S3. So in the preparation phase, the Byzantine fault tolerant protocol is run in each of the input one to lock the amount. And then once the lock is done, this needs to be notified to all the other shards involved in the transaction, like this one will be notified to this and this one. And after all the locking is done properly, then the transaction can be finalized. So they will actually transform the lock into spent coins, and this will do the BFT to receive the coins. So the issues with this is that we basically cannot remove any of this BFT run without, hindering the atomicity, compromising the atomicity. On the other side, this two-phase commit has another issue that is basically cannot withstand the silence attack. So basically it means that if we have a malicious node here that is not forwarding the information to the other nodes, this is basically not working, particularly in the case of asynchronous networks. So either we have to deal with the high overhead, actually we have to deal both with the high overhead and the weak atomicity. The other issue is what is the mechanism that is used to notify the other shards that a given transaction has been confirmed inside a given shard. So for a cross-shard certification, we have two completely different approaches in terms of communication. In one approach, we have a leader-to-leader, where basically in each shard, we have a leader that is responsible of the communication with the other shards. As you can see here, this is quite optimal, I would say, in terms of communication, because only one node is doing the communication. But on the other side, we have a big issue with basically the fact that if the leader is malicious, then of course it can selectively not forward message outgoing the shards or not forward to the internal nodes the message incoming to the shards. And the other possible, completely opposite approach, more kind of resilient, will be end-to-end communication. So in this case, you can see that all input, all nodes in the input shard will communicate the information to all the nodes in the output shard. In this case, we have order of n square complexity. And the problem here will be basically the communication. So either we'll have a reliable communication or we will have inefficient communication. So at this point, there was a need for a solution that was generic for synchronous and asynchronous type of network. Of course, secure, efficient, and optimized in terms of cost. So we come up with this proposal, which is Kronos. I cannot go for time constraints into all details of the protocol, but I will try to explain with an example specifically for valid and invalid transactions. Okay, let's see how valid transaction will work. So let's assume basically we have client A and B that want to spend the blue and purple coins respectively to payees inside shard 3. So what will happen is that they will inform the payee's shard about this, this transaction with some signed information. Of course, at this point, they cannot prove that the coins are available inside the shard, but they can submit a proper request. So what the payee's shard will do will forward this information to the two input shards, and this will be put in a queue of transactions to be validated. So what will happen is basically that for each of the transactions at the point, the shard will run a BFT protocol, and if everything is correct, like in this valid transaction case, there will be in the ledger a spending transaction about blue or purple points, respectively. Then in this other phase, where all of the input transactions, input shards, need to notify the output shards, then we'll use this reliable cross-sharding badge certification to notify this that these transactions have been secured in the input. I will give you more detail in a short while. And the other, let's say, novel thing is that instead of finalizing the transaction here, we have a buffer inside the shard that will wait for all the confirmation from the input shard here. And once we have all the input shards secured in the buffer, then we will, of course, first put the transaction, as far as there is one honest client, we'll put the transaction in the waiting queue. And then with a BFT run, there will be a finalized transaction to receive money inside this shard. So in the case that we see in the slide of a valid transaction, basically in comparison with the two-phase commit, we basically need to run only one BFT instead of two, particularly for the input shard. Let's see what happens in the case of an invalid transaction. In the case of an invalid transaction, we have basically two sub-scenarios. So in the first case, here we have basically this shard where the coins are actually not available. So D was a malicious client. So we will have invalidity proof of rejection that will be again broadcast to the all other shard involved in the transaction. In this case is one input and one output shard. So what will happen? Again, we have two subcases. Subcase number one, the case of a happy path, it means that this other shard will receive the proof of rejection before running any BFT that we saw in the previous slide. So it will just abort the transaction and reject the request of payment. And similar in the receiving one, notice that we didn't put anything in the buffer, so we'll just also in this case reject the transaction. Please note that this is very likely to happen. Okay, this is very likely to happen because computing this by at least one honest node is much faster usually than running a BFT distributed protocol. So it's very likely that this proof will hit this shard before any BFT is actually computed. Okay. I'll try to go fast. In the case of an epi path, basically what will happen is that this will have done already with the BFT. So we need to run another BFT for the refund. In this case also will cost no BFT in the receiving node. So very quickly, then we can go again into the details if you like. So how we send the cross sharding certificate? Basically, we run for after the BFT on the input has been run, we group the transaction on the based on the output shard, and for each output shard, we use erasure code to build blocks, and then the blocks, all the blocks will be the leaf of a Merkle tree, and this will be sent. So each node is responsible of sending only one block, and this is the optimization, to all the receiving nodes, together with a proof, which will be the off path of the hash of the Merkle tree, and this will allow the verification on the receiver side, reconstruction of the transaction, and the buffer. I will try to wrap up. Oh, okay. Quickly on the evaluation, actually we also have GitHub repository. We went through the evaluation. You find the code available, artifact evaluation. So in terms of experimental results, you see the throughput is very high, latency is very low, and particularly when you compare our solution with the two-phase commit, you see a significant improvement on the throughput, and the latency is significantly less. And similar when we compare our solution with other sharding blockchain like AHL and ByShard. Okay, I think I can wrap up here. Here you can see the outcome. So basically, we can withstand malicious client and leader, atomicity, intra-shard blockchain, which will be just one BFT for each of the involved shards, and the cross-shard overhead will be proportional to NB delta. Okay, I think that's all. Thank you.
Thank you, speaker. And we have time for one brief question. One very brief question. Go ahead.
Thank you very much. It's a very great work. And I have two questions. Specifically, the first question is that is there any different ways to create a transaction? Because in the state-of-the-art sharding protocols, it's the payers create the input transactions, and then the output transaction is subsequently created. But in this paper, I just noticed that it's the payees that request the delivery. So does the methods to create a transaction different from other sharding protocols?
Yeah, this is actually the difference, if I got your question right. So basically, the input client will request the transaction to the payees with some basic information about the transaction. Of course, they cannot send a proof that the coins are available and not spent, because that's a task that can only be done inside the shard. So there is an initial check, but I would say it's not that important. So the check needs anyway to be done by the corresponding input shard. So transaction is initiated by here upon a request of A and B, which are the payers.
Okay, thank you for your answer. Okay, the second...
We are out of time. So you will bring Mauri for you out in the back, and then you just can ask him as many questions as you want. All right? Thank you so much. Let's thank the speaker again.
Thank you.